lots of, having children, another big baby boom, and then birth rates are going to go down. So I think that you are, the number of 18-year-olds in the country is, at its all-time high, or is going to be in 2 years when my poor son tries to get into college. And so and then it's going to go down again. So this is a cyclical thing that keeps happening over and over again with baby booms and busts. And everybody knows about the baby boom after the war, my generation, the 50s and 60s, when I was born. Everybody knows about that. But they don't realize that there's been baby boom after baby boom after baby boom. And this is a cyclical phenomenon. And then the thing they really don't know is that it's exactly the same as the stock market. That the stock market followed, those 5 patterns in the stock market were the same patterns of the baby boom. Okay, so I'm going to end with that picture. So, okay, so a picture is worth 1,000 words, but it's not that compelling an argument. You need a little bit of analytics. Suppose everybody knew that generations were going to get bigger and then smaller and then bigger and then smaller. Would the stock market go up and then down and then up and then down, as I was saying and as all these newspaper columnists were saying, or would it just stay the same as these less imaginative economist critiquers were saying, that it couldn't have anything to do with demography, because by rationality people would look forward and they'd anticipate it going down, and so they'd all sell before it went down so it would never go down. And okay, so it turns out it does go up and down. Okay, and that argument the economists gave doesn't make any sense, because they were implicitly assuming that the rate of interest stayed the same the whole time. And if the rate of interest doesn't stay the same, then there's no reason why the stock market has to stay the same. So let's go back to where we were before and change the model a little bit. So let's suppose that the model is an alternation between big generations and small generations. So let's suppose that you have 6-2, 3-1, and 6-2. And I think I kept, so it's a good question, what should I do with land? I think I kept it at 1 every period. God, I hope that wasn't the key to the result. Okay. So in the paper, of course, I had, people living 80 years, and I had their income, reflecting the sort of trend in income over the lifetime. But anyway, for the purposes of this class, let's say there's a small generation where it goes, young 3, old 1. Then the next generation, which is just 2 guys, so they're both 3-1 guys, so in aggregate they're going to be 6-2. The next generation is 3-1, the next generation 6-2, the next generation is 3-1, and it keeps alternating like that forever. Okay, now, how would you solve for equilibrium? Does the whole thing get just much more complicated? I mean, what happens after all? Are there any questions here about what we're doing? So it looks way more complicated, but it's not. It's a little bit more complicated, but not much. You can still solve for this. Okay, so I'm going to not spend too much time on this, but I'm just going to show you what you would do. So what would you do? Well, by symmetry, I claim you can guess that there are going to be 2 prices. So you notice that every generation only cares about the relative price between when it's young and when it's old. So there's this relative price. That relative price between consumption at time 1 and time 2, that's going to affect the generation born at time 1. It actually has no effect on any other generation. These generations are born after that. So this interest rate, this relative price between these 2 periods, affects only one generation. Okay, so this generation is affected by the interest rate between time 2 and time 3. This generation is affected by the interest rate between time 3 and time 4. Every generation is responding to the interest rates during its life, not during another generation's life. So by symmetry, I think you could guess, and it turns out to be true, that there's going to be a price, a relative price, I should call them small, relative price for the small generation and a relative price for the big generation. Okay, and the same thing is going to happen. So this is going to be, this relative price will be P small, this will be P big, and then we'll get P small again here. and P big connecting these guys. And it's just going to keep repeating itself over and over again. And by symmetry, you could guess that the equilibrium would look like that. Is this making sense? It's not making sense. Is it making sense? So what would I have to check to see that there's equilibrium? Well, any generation. So let's do it over here. Let's do a small generation. Oh, okay, so we never did the first. So the first generation, yeah, it depends on whether we start with a small one or a big one. But remember, if we can clear all the markets for all time except the first market, that one has to automatically clear. That's Fisher also, that was Walras's insight. Okay, so we know that if we can clear all these, the first one's going to look very different, but it's going to clear anyway, so I don't really have to worry about it. So we'll see why that works. So what are the generations? So I'm going to now talk about market clearing at any time except the first one, which is more complicated. The first one seems really complicated because there's this guy Zero who owns these dividends that go on forever. But of course, they're just worth the price of land, which he's going to sell off. So, but anyway, we'll come back to that in a second. So in every generation, every time period, you're either going to have when small generation is young. Okay, what do you get? What's the market clearing equation going to be? Well, the small generation is going to be young. So that means the old generation is big. Sorry, so there's a half here. So the big old guys, their endowment is going to be it's going to be 6. There are 2 of them. So I can multiply. I can put the 2 out here. 3 plus 1 P big. Okay, divided by P big. That's the big old generation. Plus, in the young generation, there's just they're the usual 3 plus 1 P young divided by 1. Okay, has to equal. Now, how many endowments do we have? We've got 2 old guys plus, each owning 1, so that's 2 times 1, that's their endowment, plus 3, that's the young guys, plus the land dividend, so that's 6. So this should be P small, not Py, P small. No, I don't, because the old guys, the big generation is old, so small generation is young. So the young generation, they're consuming in their youth now, so they're looking at their endowment. The price when they're young is 1. So their young endowment is 3. Their old endowment, their income is 3 times the price to them of 1 when they're young, plus the endowment of 1 when they're old times P small, divided by the price when they're young, which they're thinking of as 1, right? They only care about the relative price between young and old. And that relative price is determined by P small. So I could call it PT and PT plus 1, but I know that ratio is going to be P small. So really it only depends on the ratio, so I might as well just use the ratio, P small. This is a crucial idea that I've used 100 times, and I think I've used it now, 3 or 4 times anyway. So, but I think some of you don't quite know what the hell I'm talking about. So somebody asked me a question if they don't know why this is right. Whoever just asked it, maybe you still don't know why it's right. Who asked this question a minute ago? Yes. Do you understand how I got this, or you do? Okay? But when the old guys, see the old guys, which is the big generation, we're clearing time, we're looking at this time. So the total endowment is 3 for the young generation. Their endowment is 2, and the 1 unit of land, that's where I got the total supply of 6. So this generation, when it's young, they care about the P small, the relative price between here and here. And so they're looking at P small, the relative price of 1 to P small. The old generation, at the same time, is looking over their lifetime at the ratio of consumption here to here, which is given by P big. So they've got a P big here, and they're consuming when old, so they're dividing by P big. Okay? But now we've got a second equation, which is when big generation is young. So why don't you tell me what that equation is going to be? How much is the endowment when the big generation is young? So that's maybe clearing at this time. Here the big generation is young. So what's the endowment? It's going to be the young. So the old, there's only going to be one old guy. There are going to be two young guys. Each have endowment of 3 plus 1 unit of land. So that's 8. And you can see that adds up to 6 plus 1 plus 1 is 8. Okay, and what's their demand? What's the demand for the two? So there's the old. What are the old going to be doing here? It's in this generation we're doing the market clearing. Somebody knows how to answer this. Yeah.
Don't they have 2 when they're old as well? So 2 times 3 plus 2.
Over here, the small generation only has 1 when it's old.
Big generation.
But big generation, that's over here. We're clearing at this time period. So there's a bunch of young guys and just a few old guys.
Oh, okay.
So the endowments are 6 plus 1 plus 1. The time is going that way. So that's why that's an 8 over here. 1. So 1. So this is the 1 old guy's endowment. 2 young guys who have 3 each. That's endowment of 6 plus the land is 1. So you get 8. That's how I got an 8 over there. That's the supply. So what's the demand? Who's trying to buy the stuff? What's the demand of the old guys?
They're going to spend all the resources they have.
So, and that's going to be what? They're planning to spend when they're old. Okay, we're doing this one. So when the point of they make their plans when they're young. They anticipate what the prices are going to be, and so how much do they plan to spend when they're old? 3 plus 1 p what? P what? What p? P small, exactly. Over p small plus, what are the young guys doing? We're over here. So 2, there are 2 of them. What's this? P what? Big, divided by, oh, there's a half here. Yep. Over what? 1. Okay, exactly. So that's it. So there are 2 equations and 2 unknowns, P big and P small, and 2 equations. So to solve this whole model, you could get 2 equations. You just have to solve these 2 simultaneous equations, which I did. Okay, now, and then you can find the effect. So all these old economists, the economist critiquers would say, well, P big should equal, okay, what will be the price of land, by the way? So what's the price of land going to be in the end? What's going to be the price of land, according to Fisher, at time 1? At time 1, let's say. So right here, what's the price of land? Remember, it's the price after the dividend is paid. So what's the price of land? Let's do the present value of the discounted dividends. What would it be? Maybe I better write it over here. Remember, the dividends are just 1 plus 1, 1 plus, so there's going to be 1 plus 1 plus 1 plus 1, but I'm going to be discounting, I'm going to be multiplying by something. So what is the price of land? P small, incidentally, equals, I could always write that as 1 over 1 plus R small. And I could write P big as 1 over 1 plus R big. Okay, so what's the price of land going to be? So it's the price of land starting here just after the dividend is paid. So it's very, it's hard to think about this. But if you can figure this out, then you've totally understood everything in the course, because this is so much more, it uses all the ideas in a just way more complicated way. Yes?
It's a geometric average of R of small and R big.
Well, start telling me the formula. So if I want to multiply, if I want to do the first terms, what is this first term?
It's R small.
So you would put 1 plus r small here. Okay, and now what would you put over here? What?
1 plus R big.
You'd put 1 plus r big here.
Times 1 plus R.
Okay, very good. So now you guys really know what's going on. And what would you put over here?
Times 1 plus R small.
Okay, exactly. 1 plus r small times 1 plus r big times 1 plus r small. Okay, that's that one. I'm going to stop with that too much. Okay, plus dot, dot, dot. Okay, so you have the idea now. What's the idea? Discounting between, you're taking the present value of all the dividends. So this dividend, you have to discount it by 1 plus r small. This one, you have to discount it twice. First to bring it back here, that's 1 plus r big. Then to bring it back here, that's another 1 plus r small. So 1 plus r big, 1 plus r small. The third dividend, you discount first at the small discount, then at the big discount, then at the small discount. Just like that. You keep adding them. So why should the prices, what if you look at the price of land at time 2? Is it the same number as that? Is it the same formula? It's not the same formula, because at time 2, you're starting here, and the first discount is P big. Okay, so it's going to be 1 over 1 plus R big plus 1 over 1 plus R big times 1 plus R small plus 1 over 1 plus R big times 1 plus R small times 1 plus R big plus dot, dot, dot. So this isn't the same as that. Okay, it would only be the same as that if R big was equal to R small, if P small was equal to P big. So which one do you think is so which one do you think is bigger? You think P small is equal to P big, or one of them is bigger than the other? And why? That's the answer to the critic's puzzle. So you see, you've taken something that appeared in the newspapers. It sounds like common sense. If there are all these middle-aged people like me bidding up there were so many of us who want to hold stocks. We're at the peak of our earning power. We've got tremendous amounts of money. We want to, what are we going to do with it except put it into stocks? You'd think common sensibly the price of stocks would have to go up. When we get old and we're selling all our stocks, you'd think the price of stocks would have to go down. Okay, so that would tell you that the interest rate was going to be bigger or smaller. So that would suggest that the price at time 1, when the small generation was young, would be low, and the price at time 2 would be high. Okay, and that could happen if this interest rate was low and this interest rate was high. Okay, but does that happen or does that happen? You can't know until you solve it in the model. The critics said, oh, that can't be right because somehow, the price should even out and everybody will be looking ahead and buying or selling at the right time. You can't buy and sell at the right time because you're going to be dead. So you don't have much choice except when you're young here to save and when you're old here to dissave. So, they seem not to have overlooked that small problem. So anyway, okay, so the point is that to know the answer, you can't just reason it out verbally. You have to write down a model, solve for the model, and see what happens. And sure enough, it happens like, okay, so we'll go back to the paper now. Well, okay, if there are any questions about this? Okay, so all I did in this spreadsheet is I wrote down those two equations. So you see that I've got the young and the old have the same half-half log utilities. The small generation is 3:1. The big generation is 6:2. Land is always producing 1 every period, and we get two different prices. The price is called PA. That's the A generation, which is the small generation, and the B generation, which is the big generation. So you can see that PA is a very small number when the generation is small, and that means the discount rate is very high. So a high interest rate when the generation is small, and a low interest rate when the generations are big. So in the money-making peak of the big generation, the real interest rate is small, and so that means you're not discounting very much. And so the prices are high of land. And so sure enough, the price when the small generation is young is 1.29, and when the big generation is young, it's 2.08, vastly higher. So it really is the case that as the generations rise and fall, the interest rates rise and fall, and the price of land rises and falls. And everybody's rational and anticipating everything. Okay, so there really is, it really could be. I'm not saying it's true, because it could be a coincidence that these things all matched up. But the fact is, demography can have a big effect on economic equilibrium in the stock market, and you can be an economist and believe in demography. You don't have to be a Marxist or something to think demography and fertility and all that stuff is going to affect the economy. And for a long time, economics tried to wall itself off from other social sciences and say, oh, those fertility people and all those touchy-feely people, it's got nothing to do with the real markets. Well, it has a lot to do with the real markets. Okay, so one last thing. Would you rather be in the small generation or the big generation? Of course, the answer is there, but tell me why. Yep. Okay, that's correct. So I'm screwed. And so why is that? Well, it turned out to be the utility of the, this is the utility of the big generation per person. Of course, adding the two people together, it's bigger. So per person was this, a lot less than the generation of the utility of the small. So why did that happen? Why exactly is that happening? So remember, I'm distinguishing sort of your peak, I'm calling young your peak earning years, and old I'm calling the stuff when you're retired and not earning very much. So why is it that a high interest rate is good? Yes?
It encourages consumption today for the young generation.
Well, I think the point is, if you're making money when you're young and you've got a high interest rate, that means a high return. So you can make a big return through your life, whereas my generation had a very low return. The return I'm getting now is terrible. It's negative. So the return I'm getting now is just hideous. But when my parents were young, they were making an astronomical return, incredible rates of return. Okay, and they were earning money, in their younger years and investing it to save when they were old, and they're getting incredibly high return. There's nothing to do with my money. There's so many people like me pouring money into the stock market, we're getting a very bad return, and that's why it's not so good to be part of a big generation. So other people had said the same thing. They said big generations have to squeeze into the same houses, so there's less housing stock, or we build more houses, the next generation comes along, there are all these houses built for them, and there are less of them to, so they get better houses, and everything's better when you're the small generation and you're screwed as the big generation. And here's an example of it. Okay, so that's it for Social Security. All the things I wanted to say about Social Security. Now, the exam, as I say, will end with, you won't have to do the 2 generations and all that stuff on the exam. But the first part about solving for the 0.55, that one you might have to do something like that. But anyway, the lesson that, you can have a controversy in the newspapers with arguments on both sides. You never can figure out the right answer till you write down a model. And the model can be very simple, the kind of thing you could do as an undergraduate. That's the lesson I'm trying to communicate. All right, so from now on, though, we have to change gears, and I think the course gets a lot more interesting, okay? But we needed all this background basics to have the logic of finance. But finance is really nothing without uncertainty. If you don't know what's going to happen tomorrow, that's when the thing gets interesting. That's when you have to think harder. That's when people make mistakes. That's when a hedge fund can make a profit. That's when, everything gets more exciting when there's uncertainty, and we have to start adding uncertainty to our thinking about the world. So since I only have a few minutes, I'm going to spend the last few minutes just reminding you of what you're supposed to know about uncertainty, which is this slide. Okay, so it's not a very complicated thing. Where's the, I see PowerPoint. Okay, so there are two kinds of uncertainty, one of which we're never going to get to. So the uncertainty that we're going to work with in this course is everybody understands what could possibly happen. So this was a brilliant, states of the world model, it's called. So Leibniz is supposed to say states of the world right there. Leibniz was the one who first invented the idea of states of the world. He said we live in the best of all possible worlds. So if you don't know what's going to happen in the future, we're going to represent that as many potential states of the world. Now there are other ways you could model uncertainty, and philosophy is a big, a big subject in epistemology and philosophy. I'm going to stay closely to the states of the world thing. So if there's something about the world we don't know tomorrow, I'm not going to assume that it's just vague in our minds and we can't quite make it out. I'm going to assume you actually can make it out. It's just you don't know which of the possibilities are going to happen. So it's many states of the world. So a example of that, of course, is spinning a dice or spinning two dice. So you don't know, which of 36 possibilities is going to happen. Each of those would be one state of the world. Okay, so we can, so those are all the possible sums. So there are more states of the world than there are outcomes, notice. You can get 2 through 12 as the sum of the dice, but there's still 36 possible states of the world. And so that random variable, the sum of the two dice, is expressed as a function. It says in every state of the world, what is the random variable's value? So our state of the world, by that I mean something that's so detailed that it tells you the value of every random variable. So that's how I'm going to be thinking of uncertainty, that we're here today and a bunch of different things could happen tomorrow, and this is an exhaustive list of everything that can happen tomorrow. We're going to have to come back and criticize this assumption, but it introduces uncertainty in a way which is still quantifiable and not vague. Okay, so you can talk about the histogram of outcomes of the dice, how many ways, what chances are the chances of getting a 7, 6 out of 36, etc. So this is stuff I'm sure you all know. Okay, the most famous histogram in all of mathematics is the normal distribution, which I don't have time to explain. And so a normal distribution, remember, is this exponential thing. The dice example, is sort of looks like it. And in fact, if you had enough, dice and you kept averaging their outcome, it would be normally distributed. So lots of things turn out to be normal. One of the properties of normal is that the tail gets small very quickly. Okay, and so you're not going to get very many outliers. The normal distribution is a very common distribution. There are lots of reasons why it should occur all the time, and it's also mathematically very easy to work with. And so economists for a long time assumed everything was normally distributed, but an implication, as I say, of normal distribution is that it's very unlikely something extreme is going to happen because this thing goes down exponentially fast to 0. So you're almost never going to see something way out here. Yet we get these crashes fairly frequently. If every 10, 20, or 30 years or something, there's some gigantic outlier. So clearly things can't be normally distributed, and that's called fat tails. Okay, and I'm sure you've heard about that in the newspaper. We're going to come back to that. Okay, now there are a couple things that you need to know. So you can represent the payoff of any random variable as a picture. In every state, what its payoff. Okay, so a riskless random variable, riskless investment will pay the same amount in every state. So I still have a few minutes here. Okay. Okay, so now two incredibly important concepts, which I'm sure you know, or at least the mean you know. Just the average, what's the expected payoff? So the expected payoff is you multiply the outcome in every state by the probability of the state, and you add it up. Okay, so there are how many different ways? So if you have one dice, okay, you can figure out the expectation of one dice. It's equally likely to get 1, 2, 3, 4, 5, or 6. And so if you add all those up, multiplied by a 6, you get 3.5. So the expectation of one dice is 3.5. The expectation of two die is therefore, okay, so that's one dice. Okay, now the expectation of adding two dice together is, of course, going to be 7, because the expectation of one dice is 3.5, and the other dice is 3.5, and so the expectation of the sum is the sum of the expectations, so it's 7. Okay, so you know that. Now, one more thing that you have to know is the variance. So how do you measure how uncertain you are about what's going to happen? Well, the simplest number to do, like with the dice, is to say, okay, the expectation is 3.5. When we don't get 3.5, it means there was some error. Our expectation wasn't confirmed. So you could just measure the error as the distance between 3.5 and what you actually got. So if you got a 4, you could say you were off by a half. But people don't do that. They measure the square of the distance, okay? And they take the average square of the distance. That's called the variance. Okay, so it would be, if you got 4 when you're expecting 3.5, the error is a half squared. So it's, you take a 6 times a half squared, plus a 6 times 1.5 squared, plus a 6 times 2.5 squared. That's for the high mistakes. And the low mistakes, you take a half times a half squared, plus a half times 1.5 squared, plus a half times 2.5 squared. Now, why do they use the expected squared error instead of just the expected error? Well, for this simple reason, which you may not have thought of, if you had to guess, if you looked at the error as the penalty for making a wrong guess, and you were forced at the beginning to say, what guess would you like to make for how the dice is going to turn out, how the die is going to turn out, and if you're wrong, we'll penalize you by this measure of error. Well, if you're just taking the absolute error, your best guess would be any number between 3 and 4. You could say 3.5, but you could also say 3.25, because if you said 3.25, you'd become closer on all the low rolls of the dice and be a little further off on all the high rolls, and you'd get exactly the same error. So you could say any number between 3 and 4. But if you make the error the square of the mistake, your best guess is always to say the expectation. 3.5 is the only thing you can say to minimize your expected penalty if the penalty is the squared error. So because of that, that's connected to a mathematical thing, and in orthogonal vectors and all that. Because of that, the error we talk about always is the squared error. And so that's whenever we're measuring uncertainty, we're going to talk about the squared error. The average of the squared errors, or the square root of that, which is called the standard deviation. Okay, I have one more minute to just finish this. So I'm assuming you all know that, okay, or can learn that. Okay, one more thing that I'm going to assume you know. The last thing is the covariance. What does it mean to say that random variables x and y move in the same direction? So this was quite a brilliant thought. So what it means is that to move in the same direction means if x surprises you by being above what you would have expected, so if the expectation of x is x bar and the expectation of y is y bar, if you multiply the two and they're both higher than you expected, you'll get a positive number. If they're both lower than expected, you'll also get a positive number. So by taking this sum, the expected deviation from the expectation multiplied, you get a number which, when it's very positive, it means they're either both positive together or both negative together. So they're going in the same direction. If one of them is above the average while the other one's below the average, then you'll get a negative number. So big covariance means they move in the same direction. Big negative covariance means they move in the negative direction. Okay, so I'm going to take it for granted you know this, and we're going to take this up starting right after the exam, which is on Tuesday.